Hi guys, in this video, we will explore the incredible density of neutron stars, their powerful magnetic fields, and their role as cosmic laboratories. Let's dive into the mysteries of these cosmic powerhouses.
Neutron stars are born from the remnants of massive stars that undergo supernova explosions. As the outer layers are expelled into space, the core collapses, forming a neutron star. This violent process is a spectacular event that releases an immense amount of energy, spreading elements forged within the star throughout the universe. Neutron stars are therefore cosmic recycling plants, contributing to the enrichment of the cosmos with heavy elements. They are the remnants of stars that have reached the end of their lives, leaving behind a dense and compact core.
The density of neutron stars is mind-boggling. Imagine compressing the mass of our Sun into a sphere with a diameter of about 20 kilometers. A teaspoon of neutron star material would weigh billions of tons on Earth. This incredible density is a result of the immense gravitational force that crushes the atomic nuclei together, causing the electrons and protons to combine and form neutrons. Neutron stars are the densest objects known in the universe, challenging our understanding of the fundamental properties of matter. Their density is so extreme that it leads to a bending of spacetime around them, creating a gravitational well from which nothing, not even light, can escape.
What sets neutron stars apart is their immensely powerful magnetic fields, thousands of times stronger than those of ordinary stars. These magnetic fields play a crucial role in shaping the behavior of neutron stars and their surroundings. They can accelerate charged particles to near the speed of light, generating intense electromagnetic radiation in the form of X-rays and gamma rays. These energetic emissions provide valuable insights into the physics of extreme environments. The magnetic fields of neutron stars also produce astonishing phenomena such as magnetars, which are neutron stars with the strongest known magnetic fields in the universe. Magnetars exhibit powerful bursts of X-rays and gamma rays and are believed to be the source of some of the most energetic explosions in the cosmos.
Neutron stars that emit beams of electromagnetic radiation are known as pulsars. Their rapid rotation causes the beams to sweep across space, appearing as regular pulses of energy. Pulsars serve as cosmic lighthouses, allowing astronomers to study their properties with precision. By carefully analyzing the arrival times of these pulses, scientists can detect even the slightest changes in the rotation of the neutron star, providing valuable information about its internal structure and magnetic field dynamics. Pulsars have been used as precise celestial clocks for testing the predictions of general relativity and discovering new planets in distant star systems. Their precise timing has even helped confirm the existence of gravitational waves, further validating Einstein's theory of relativity.
In 2017, the merger of two neutron stars, known as a kilonova, was detected through gravitational waves. This groundbreaking discovery confirmed Einstein's predictions and opened a new era of gravitational wave astronomy. The collision of these dense stellar remnants produces an explosion of staggering proportions, releasing vast amounts of energy and creating heavy elements such as gold and platinum. Neutron star mergers provide a unique opportunity to study the extreme physics involved in such cataclysmic events. The detection of gravitational waves from neutron star mergers has allowed scientists to probe the nature of gravity and the properties of matter at extreme densities. It has also provided insights into the origin of heavy elements in the universe, offering a glimpse into the cosmic factories responsible for their production.
Neutron stars provide scientists with a unique opportunity to study extreme physics. By observing these cosmic laboratories, we can gain insights into gravity, nuclear physics, and the behavior of matter under conditions impossible to replicate on Earth. The immense gravitational force near the surface of a neutron star can create conditions similar to those found in the early universe or inside the core of a supernova. Scientists can use these observations to test and refine theories about the fundamental nature of matter and the behavior of particles under extreme pressures and temperatures. Neutron stars act as natural laboratories for understanding the physics that governs the universe. They provide a window into the fundamental forces and the behavior of matter in some of the most extreme environments imaginable.
Within neutron stars, exotic states of matter may exist. Strange matter, composed of quarks, is one possibility. It suggests that under the intense pressure inside a neutron star, the individual quarks within protons and neutrons could be liberated, forming a new state of matter. Another intriguing hypothesis is the existence of quark-gluon plasma, where the fundamental particles that make up protons and neutrons are no longer confined. Studying neutron stars can help explore the existence and properties of these exotic forms of matter, providing crucial insights into the fundamental building blocks of the universe. By studying neutron stars, scientists hope to unravel the mysteries of the strong nuclear force and the behavior of matter under extreme conditions.
Observing neutron stars requires advanced technology and innovative methods. Ground-based observatories, space telescopes, and gravitational wave detectors all contribute to unraveling the mysteries of these cosmic objects. X-ray and gamma-ray observatories, such as NASA's Chandra X-ray Observatory and the Fermi Gamma-ray Space Telescope, provide detailed images and spectra of neutron stars, enabling scientists to study their magnetic fields, surface temperatures, and emission properties. Gravitational wave detectors, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, help detect the ripples in space-time caused by neutron star mergers, providing unique insights into their physical properties. Future advancements in technology and observational techniques will undoubtedly bring us closer to understanding the complexities of neutron stars.
While we have made significant progress in understanding neutron stars, many questions remain unanswered. How do these dense cores maintain their stability? What happens to matter as it gets crushed to extreme densities? How do the magnetic fields shape their surroundings? Scientists continue to develop and refine theoretical models, conduct observations, and perform simulations to address these questions. Future discoveries and advancements in observational techniques hold the potential to shed light on these mysteries, deepening our understanding of neutron stars and the fundamental laws of physics. Every new piece of information unraveled about neutron stars brings us closer to unlocking the secrets of the universe.
Neutron stars continue to captivate astronomers and physicists alike, challenging our understanding of the cosmos. Their unimaginable density, powerful magnetic fields, and potential to unlock secrets of the universe make them a fascinating subject of study. By exploring neutron stars, we delve into the extreme physics that governs the universe, providing valuable insights into the nature of matter, gravity, and the fundamental forces. Through continuous research and exploration, we hope to unravel the mysteries of neutron stars and gain a deeper understanding of the vast and awe-inspiring cosmos. Keep exploring, keep questioning, and keep seeking knowledge.
Thank you for joining us on this journey through the captivating world of neutron stars. If you enjoyed this video, don't forget to like and subscribe to our channel for more captivating content about the wonders of science. Together, let's continue to unravel the mysteries of the universe and expand the horizons of human knowledge.